Hello, welcome back to my channel. In today's video, we're going to be diving into one of the most important reactions in organic chemistry, which is the SN2 reaction. By the end of this video, you will understand how it works, what affects its rate, and why it's called bimolecular substitution. Let's get started. So SN2 stands for substitution nucleophilic bimolecular. And that means that two molecules are involved in the rate determining step, the substrate and the nucleophile. So what makes SN2 unique? It's a one-step mechanism, no carbocation intermediate. Secondly, the reaction rate depends on both the nucleophile and the substrate. That's why it's bimolecular. The third reason why it's unique is that it causes inversion of configuration at the carbon center. So imagine umbrella flipping inside out. Okay, so these three things makes it unique. The next thing we look at are the factors affecting SN2 reactions. The first one is the substrate. So since we say that it is bimolecular, which means that the rate depends on both the substrate and the nucleophile, of course, it's expected that the substrate structure affects the reaction. So primary alkyl halides react the fastest, with the tertiary ones barely reacting at all. So this is a primary alkyl halide. Now, primary means that this carbon that is bearing the leaving group is connected to only one other carbon. That is primary. So primary alkyl halides tend to react the fastest. We also have what we call the methyl, which is the CH3Cl. So this is a methyl halide. Now, methyl halides react very fast. So they are faster than primary alkyl halides. Now, primary alkyl halide is much more faster than the secondary, and secondary is faster than the tertiary. So this is how we rank them. So primary alkyl halides will react the fastest compared to the secondary and tertiary ones barely react at all because of steric hindrance. Now, when it comes to the strength of the nucleophile, the stronger the nucleophile, the faster the SN2 reaction. So stronger nucleophiles like OH negative, CN negative, and much more will speed things up. And then leaving group ability, better leaving groups like iodide or bromide will make the reaction smoother. And then the last factor is the solvent. So for SN2, polar aprotic solvents like acetone, DMSO, DMF will favor SN2 reactions because they do not stabilize the nucleophile too much. So these are the factors we need to look out for when doing SN2 reaction. Let's look at this example. So before we start, this is known as the substrate, while this here is the nucleophile. Now, in the substrate, you have the leaving group, which is this I. That will be our leaving group. Now, SN2 reaction happens in one step only one step. So a nucleophile, in this case, this is our nucleophile. So I usually like putting my lone pairs when I do mechanism. So this nucleophile is an electron-rich species, and it will attack the electrophile. So the electrophile is this carbon. That's the electrophilic site. So it's going to attack this electrophilic carbon that's bonded to the leaving group. So it's going to attack it from behind. It does what we call a backward attack. So when it attacks that, this would break off. So on this side of the reaction, the OH would take the place of the leaving group. Every other thing stays the same. And the leaving group would then be like your byproduct. And that is it. One-step mechanism. The nucleophile attacks, the leaving group leaves, and the product forms. Now, this is another example. Here we have the substrate, okay, and then we have the leaving group, we have the nucleophile, and this is our polar aprotic solvent. So everything here leads us to SN2 reaction. We have a polar aprotic solvent, we have a strong nucleophile. So strong nucleophile would favor SN2 reactions. So we would usually remove the Na. This is positive end and that's the negative end. It is a negative end that does the attack. So I'm going to write this out. So this is how it's going to look like. Okay. So this is going to attack again from behind, backward attack. When it attacks, this leaves. Now on the product side, we're going to have an inverted product. So this was originally a dash. Our product is going to be a wedge. So this is going to then be SCH3. The nucleophile would replace the leaving group. And then this stays the same, okay? Nothing happens to that. And that is our major product. Of course, the Br would be here. The sodium has been hanging around somewhere. Because it's positive, it will usually combine with this. So you can have it as sodium bromide. And that is it. So that's what we mean by inversion or inverted products. So to recap, SN2 reactions are fast, they are clean, and they are predictable. Now remember, we have backward attack, inversion of configuration, and dependence on both reactants. The rate law would be K times the concentration of the substrate and that of the nucleophile, because this is bimolecular. If this helped you understand SN2 reaction, drop a like, subscribe for more organic chemistry content, and let me know in the comment what topic you would like next. And thank you so much for watching, and do have a wonderful day. Bye-bye.